linear. What does this mean? If you're in the silicon business and you've got to make rib or fib hardware, what you're worried about is exponential or massive explosion that doubles. Because we can make bigger hardware every year, but we can't make it double in size every year. It's getting a little bit tough. So growing by a linear rate of 54,000. The number of AS numbers growing by 3,450 a year. For some reason, here in Asia, you don't use your own autonomous system number. Just don't. Or most of these ASs actually come from North America and in Europe, which around about 10 to 1 is the ratio. So most of that expansion actually occurs in places that are not local here. Here, you simply just push your routes into your upstream and use their autonomous system number to advertise it. Very bouncy. Advertising more specifics. Colouring the net with more specifics of aggregates. You're not getting any smarter, you're not getting any dumber. You're just doing the same old thing. Around half the routing table is more specific of everything else. So if you've got your 660,000 entries in the fib, you actually find that around about 300,000 of them don't contribute new reachability, they just qualify other reachability that's out there. Basically traffic engineering. This is the first piece of evidence here, though, of address exhaustion. January 2012, the average address announcement in BGP spanned 6,500 V4 addresses, whereas these days it's down to 4,500. So that's how you're managing to cope with exhaustion. You're just advertising smaller and smaller and smaller prefixes. So now you're down to 4,500 average addresses per announcement. It will keep on coming down. The rate you're going, you'll be down to a /24 in a couple more years, because that's the way you cope with exhaustion. This is the one thing that actually shows it up here. That's actually the span of addresses in the routing table. And as each RIR ran out, the growth curves flatten out, because there's simply fewer and fewer addresses. So we're doing okay. But this last one here is perhaps the most crucial graph for the performance of the routing system. BGP is a distance vector protocol. What that means is the way you flood information is you tell your neighbour, who tells their neighbour, who tells their neighbour, and so on. If those chains of rumours get longer, BGP takes more time. The chains are tight and small, BGP is as fast as it ever was. The average AS path length that I see is around 5.7, but I'm hanging off the edge of the internet. Closer in, the average AS path length has been steady at around 4 for a couple of decades, and that's really good news. That's what makes everything work. So what's happening with routing? Nothing. Nothing exciting. One of those talks that kind of goes, yeah, right, move along now. Despite some uncertainty about address availability, you haven't gone mad. You know, the number of routes is still quite predictable. We're heading up to around 700,000 entries in the default free zone, and we're pulling in another about 55,000 new routes every year. That's okay. Address exhaustion hasn't really changed things. So, what are we doing now that we've run out? Well, we're recycling addresses. In actual fact, the routing system can show what's happening to some extent. What I'm trying to figure out is whether what's driving this is transfers, last/8 policies, or leasing and address recovery. And one of the ways to actually find this out is to look at the profile of addresses that were added each year. So in 2010, which was the last year when we were doing address allocations, if you look at the age profile of all the addresses announced in 2010, most of the addresses are less than 1 year old. You got them from a registry, you put them in the routing system. You didn't bother bringing old addresses back to life. You simply used new addresses from the registry because the registry had them and it was so much easier. But we started running out of addresses. And over time, you've had to look in older and older pools to mine those addresses to feed the continued growth in V4. So last year, 2016, 24%, only 1/4 of addresses that we saw were actually allocated from the registry in 2016. A lot of those were from Afrinic, the last regional internet registry that still has large pools of addresses to give out. Almost all the other addresses that we saw come from our past. Interestingly, 40% of those addresses come from the dim, dark past more than 20 years ago. In other words, they were allocated before 1997. So we're actually going back to the old B's and the old A's, recycling them into the routing system. So over the years, because that's a plot for every year, that's become more and more prevalent. And last year was kind of quite a severe year. Blacknick has about 1 year to go. That curve will keep on changing. So here's another way of looking at it. And these 3 lines show you the amount of addresses in blue that have left the RIR system and are out there in userland. The number of addresses that are advertised is in green, and the number of addresses that we've allocated, but we can't see them, is in red. Okay? Let's look at the red last year. The number of addresses that were allocated but not advertised started the year at a little over the equivalent of 48/8s. By the end of the year, with half a /8 smaller. We put them together, get a full picture of what exactly we did. The RIRs allocated a little over 1/8, but they also recovered from the old unadvertised pool around half a /8. That's the recovery margin. Kinds of shows that to some extent now you're getting desperate. You're going and looking at all those old address pools going, I'll buy them, I'll take them, I'll advertise them. So that's just the same thing in words. V4. But as you may be aware, there's more to the internet than V4, there's also V6. And this is an exponential graph. So the V6 guys should be deliriously happy. Celebrate V6, wonderful. World V6 Day had an obvious impact on the growth of V6, didn't it? There, if you look very, very closely, just in there was World V6 Day. I don't think it made an ounce of difference myself. The major trend in the routing table was always going to go like that. Here's the same kind of information. The routing prefixes are growing by around 6,000 entries per year, which compared to V4 is around 1/10. But it is growing. It's not a number that's constant. Next year we expect to see more. The number of AS numbers is now 1,700 ASs per year, which is actually at half of the V4 growth. And again, the number's slowly getting larger. So to some extent, V6 is catching up, but it is taking some time. More specifics, 1/3 of the routing table. So the same badness. The average size of an advertisement in prefix size is actually getting smaller. The average address span growing at a linear rate, and the shape of inter-AS connectivity is actually much the same as V4, relatively flat. Relatively flat. So overall, 6,000 entries a year in growth, about 1/10 of the V4 rate. The AS growth rate is about 1/2 of the V4 rate, so. So what can we expect? Well, it's hard to make predictions. Because we've run out of addresses, the behaviour is not quite as predictable. We actually don't understand the transfer markets. don't understand to what extent there are addresses to recycle in routing. So it's taking a little bit of time to actually understand that. Here's the growth rate in V4 per day, daily growth rate. And if we try and bound that a little bit, we can now actually understand that it's converging into a relatively constant rate of change at approximately 150 entries per day. In relative terms, these are percentages, relative terms, it's flattened out. So that's around 3% of growth per year, what's going on in V4, and it's relatively linear. So what does that mean? Well, that's the predictions. So if you're looking to buy a router today that handles a full internet routing table, then you're going to have to look at a router that by 2022, because 5 years is not a long time in the field, but in 5 years it needs to be able to handle basically 1 million entries in its fib to do the job. If you're using IBGP and you have internal routes, add more. Now, is that a scary number? Not really. Scary numbers are when they grow bigger than Moore's Law, when they double in under 18 months. This is not a particularly scary number. But on the other hand, if your hardware that you're currently using doesn't handle 1 million entries in the fib table, its expected service life is less than 5 years. You're going to have to do something. Either drop some routes, run a default, get new equipment, do something. So that's in V4. What about V6? Growth rate slowly growing. So a growing growth rate, if you remember your maths, means a growth that's a polynomial rather than linear. It's increasing. Whether it's exponential or polynomial is a little bit harder. Relative growth rate declining. Oh, looks more polynomial than exponential. So what does this mean? The switch to V6 is erratic. It's not everywhere all of the time. There's a fair deal of growth, but it's not uniform. So predicting is extremely hard. Currently, we have 35,000 entries in the routing table. At its most optimistic, that's probably going to be about 150,000 entries in 5 years' time. At a linear rate, which is, I think, the bottom end of the curve, around 75,000. Don't forget that in your fib, you're carrying 128 bits of addressing. So the true hardware requirements, TCAM size, that's the equivalent of 4 times a V4 rate. So the 5-year time for this is the equivalent of 600,000 V4 entries, 150,000 at 128-bit. So to some extent, if you're doing dual stack, you need the equivalent of around 2 million 32-bit entries in your fib, broken up as 1 million in V4 and around 250,000 less in V6. If you haven't got that, you need to think about what you're going to do, because these numbers are relatively confident. Not completely, relatively. But again, though, they're not Moore's Law crazy. Your routers aren't going to melt, nothing terrible is going to happen yet. But that's not the only story, because not only is BGP all about your fib, it's all about updates and convergence. This graph is the update activity since 2007, or 10 years. The top line is the growth of the routing table. The bottom lines are update activity. That, anti-gravity. That shouldn't be happening. Distance vector protocols should get noisier as you put more things in. The noise rate should actually get worse, and that the update rate should increase faster than the population. BGP is doing none of that. It's actually relatively constant. There are many theories as to why this happens, but nobody knows exactly what's going on. They have no idea. But it's really good, and whatever you're doing, don't stop doing it. But we have no idea exactly what it is that's keeping that at a constrained rate. Because this thing is really why BGP is magic. Since 2007, The average time for an instability event in the routing system, converge and stabilise, has been just under 50 seconds. The number of routes has increased from 100,000 to 600,000, but the convergence time has hardly moved. That is a mystery. Like, it's really good, and it's the one reason why we're still using BGP, but it's not obvious why BGP is behaving like that. So again, nothing much unless you're a research student. If you're a research student, you should be looking at why this is going on, because none of us have a clue. V6, noisier. The update rate is actually at times much faster than the rate of prefixes. Whatever you're doing in V4, you're not doing in V6. Whatever you're doing in V6 is weird. So what are you doing in V6 that you're not doing in V4? Tunnelling? V6 over V4 ad hoc techniques? This is obviously that kind of result. That doing those kinds of tricks of encapsulation and tunnelling takes an inevitable cost in the stability of routing. Not a good idea. Look at the convergence numbers. Not 50 seconds anymore, is it? The routing performance in V6 is indeed crap. Now, it's do you hate your customers? Put them on 6. Either that or get your routing shit in order, because this is unacceptable to anybody. Routing system's just a complete mess. Updated prefixes per day, getting noisier. I'm not quite sure exactly why. And the number of updates per event. Lately, when things go unstable, normally it's 1 or 2 convergence events gets you back to stability. But some days it's up to an average of 100 updates to actually bring it to convergence. Each update takes a 35-second MRI interval. That's an enormous amount of time. 50 seconds to get stability and convergence. So the V6 BGP system has indeed got enormous issues in terms of stability and performance. But not everybody. Only some of you. Because when you do a distribution graph, what you find is that the top 2% of people contribute 2/3 of all the updates in V6. If we knew who those top 2% were, we could take them out. So here they are. In the Iran tradition of naming and shaming, anyone here from Indosat? Good, you should be working on your routing instead, because it sucks. There's another one from Indonesia, XL Indo, Permai. There's an awful lot of Indonesia there. Numbers 1 through 7. Number 8, Brazil, and then Netflix. Where's Dave Temkin when you need him? These are the noisiest prefixes out there on the net, and those are the update rates. None of those should be happening. Mike, quite frankly, when a prefix is doing 50,000 updates in a day, it's hardly delivering service, it's doing route flapping. So if you're on the list, do something. If you know someone who's on the list, tell them they're on the list and they should be fixing it, because this is not doing anyone any favours. Interestingly, V4 is the same. That even though it's relatively well behaved, in V4 there's again a small number of prefixes that are phenomenally badly behaved. So it's not just V6. That's a lot of what we find in the internet. Most of the time, most of the network is actually well understood and relatively stable. But when it goes bad, it goes horrendously bad. And you get into these uncontrolled flap update rates where the prefixes just will not stabilise. So, very similar. V4, mostly stable most of the time, but the aberrants are incredibly aberrant. That high instability actually knocks out all the figures, which is why ultimately V6 appears far worse than V4. So what can I say? Basically, we thought back in 1990 that there were 2 things that were going to kill us and the internet. We were going to run out of V4 addresses inside 4 years. The routing system was going to melt inside 4 years. We used V6 as being our response to running out of addresses. And in the routing system, the only change we made, and there was only one change, was to actually route classless, to get rid of the old A's, B's and C's and actually allowed you to route anything you wanted. It's still BGP. Still BGP. And almost 30 years later, BGP has scaled. No one expected this. Absolutely no one expected this. So realistically now, we're still doing fine. What's going on is that the advanced instability we're actually seeing is actually due to a small number of players being phenomenally unstable. That's how much you're doing a fine job. That's it. Any questions?
Hi, Jeff. When you showed the slide of the new addresses coming into the system and that slide?
I'm waiting for the video to go back to the slides. I'll get back.
Yeah, the one with the new slides, new prefixes coming to the system. No, the one before. One with the like 28% new addresses versus. Oh, that one, yeah. That's this one. So when you say the addresses are coming from legacy pools, are you including, are these gone through the registry transfer process or they just showed up on the?
Let me give you an advanced kind of peek into another presentation I'm doing later in the week on addressing. So of the addresses that moved, there's actually a bigger lot. These are the new ones, the ones that got added. But some addresses got removed and some just rehomed. So I was sort of thinking, you know, if an address moved, that's a strong indication of a transfer as being possible. And so I started looking at, of all the addresses that moved, including this lot, how many are in the transfer logs? Less than 10%. So 10% of these are in the logs, the other 90%, the registry is unchanged. I have no idea, if you will, what happened. They could have been transferred, they might not. The registry system can't tell us. So in that respect, the registry system is a poor way of looking at this. The transfer logs don't seem to capture what's going on. And it's not clear why, because it's not clear.
The follow-up question to that is, obviously there's a lot of IP address transferring going on. When I look at it, one of the biggest problems is, especially the legacy ones, you cannot figure out who's the real owners of those addresses that you're buying if it's not actually getting transferred back into the system.
Let me, I suppose, cut to the chase. There are two issues flying around. One, I believe RIPE do not register in a transfer log the movement of legacy addresses. Bit of a bummer. I don't know why, but you know, that's RIPE. RIPE NCC, it's not me.
Some right people here.
They're right. No, they're not. They're hiding.
Anyone want to answer?
The second thing, if I lease an address from you, it's not a transfer. And we are aware that there's a lot of leasing going on. And quite frankly, I think the address policy folk should seriously consider understanding how we can represent leasing. Because the more movement that happens without a registry, the more you are reliant on lawyers not lying to keep the integrity of the internet running. Now, I don't know about you, but that statement scares the crap out of me.
I was just about to say lawyers not lying.
Lawyers not lying, yeah, right. Thank you. Thank you.
Okay, thank you, Jeff. And then let me invite Rob Snyder. He will present about the new business attribute.
Thank you. There we go. My name is Job Snijders. I work for NTT Communications, and I'm honored to be here today to talk with you about a new development that has been happening in the BGP world. We'll talk about large BGP communities, which is a successor to the normal or classic communities as we use them today. And in this presentation, I'll cover existing community standards, large communities themselves, what you can do with them, and I'll cover alternative approaches that have existed over the number of years. Help? Next slide, please. Oh, there we go. So BGP community more than 20 years ago, and they were specified because we needed, as operators, we needed a better way to manage our networks. For instance, you previously had to classify through a static list of prefixes on every router which prefixes are your customer prefixes. But with BGP communities, you could tag those prefixes once and then reuse that information on the far side of the network. This greatly simplified BGP operations. And an example of a BGP community is, for instance, 2914:420, which in NTT's network triggers a certain action. And we'll go into that later. Then in 2006, a different large BGP called extended communities. And the idea with extended communities is that there's all kinds of types of communities that do different things. With normal communities, there's only one thing, there's only one type, the community. But with extended communities, there's hundreds of types. In fact, there are so many types that I would argue that for internet routing purposes, it is not trivial to see the forest through the trees. There we go. BGP communities are predominantly used for traffic engineering and ensuring that the proper peering partners receive the proper prefixes. And it's really small on the screen, but on the left side you see all kinds of examples from NTT's network. For instance, if a customer attaches 2914:435, it means that outside the country in which we received the route, the local preference is lowered to something below our default. And there are hundreds and hundreds of documented tricks. On the right side, you see a list of networks that have published their BGP communities, their manuals, so to speak, their policies, what community does what. And we can understand from this that communities are the de facto way to signal meta information between networks. Not extended communities, it's the 20-year-old standard that we use today to operate our networks. And many of our customers actually demand that we deliver this style of functionality, otherwise they will go to one of our competitors. But along came a problem. We knew that we would eventually run out of 16-bit ASNs, the ASNs in the range from 1 up to 65,000 something. So in 2001 already, and I was still in high school back then, or maybe even elementary school, people started working on defining a bigger ASN thing. And eventually what came out of that was 32-bit ASNs. And this was standardized in May 2007. This is 10 years ago. Fast forward to 2017, we see that roughly 1 out of 5 ASNs in the default free zone is a 32-bit ASN. 20% of the current ASNs, so that's roughly 10,000 ASNs, and that number is growing because IANA ran out of 16-bit ASNs, and one by one, each of the RARs is depleting their pool of 16-bit ASNs, and by default, most RARs are handing out 32-bit ASNs to their members. And now comes a challenge, because with BGP communities, classic communities, those are a 32-bit construct, and the first 16 bits are your ASN, and the last 16 bits are whatever you want it to be. And everybody can see that you cannot fit a 32-bit value in a 16-bit field. It doesn't work. So that's a big problem. And this problem, in fact, was already recognized 10 years ago in the very RFC that specified 32-bit ASNs. So we came up with a solution to this problem called large BGP communities. Later on, I'll show what a large community exactly looks like and how they compare to normal communities. But I want to tell you that I believe that this will be the successor that we'll be using the next 20 years, simply because it can accommodate 32-bit ASNs in a way that classic communities cannot. Other than large communities, there were also efforts over the years to address the fact that communities are too small. But some of these efforts were not ideal. For instance, there was the 4-octet AS-specific BGP extended community, and you can hear that it rolls off the tongue very easily. But the problem with that type of approach with extended communities is that you cannot fit either 16 bits plus 32 or 32 bits plus 16, but you cannot have both. So from an operational perspective, that type of approach never gained popularity. In 2002, flexible communities came along. And flexible communities not only address the problem of the size of the communities, but in fact it brought a great many new features. And wide communities was also along these lines. With wide communities, you can even put routing policy in a NetFlow style format inside the wide community, and it's a very advanced, complex system. And I believe that neither of those approaches benefit internet routing operations. Advanced tools are fantastic in your own fully controlled environment. But the moment you have to interact with other networks that may not speak your language or may have very different experiences or philosophies how to run a network, then simplicity is a virtue rather than a disadvantage. So when large communities was promoted inside the IETF, many operators saw the value that it brought, and hundreds of them participated in discussions in the IDR working group. IDR is responsible for the BGP protocol. In fact, 5% of all emails ever sent through that working group in its 20 years of existence were about large communities. There is a saying that the amount of noise generated regarding an idea is inversely proportional to the simplicity of the idea, and that is what we saw in this working group. People apparently could not believe that such a simple solution was what actually was desired by our community. But we got it through. And large communities have ended up just like classic communities, but bigger. And this is all you need to know about large communities. It's the same, but bigger. The design goals were to not increase the functionality of communities, not to replace FlowSpec or do anything remotely similar to that. It was just an entirely opaque approach. And opaque means that you and I, beforehand, have to agree on the meaning of a community. My communities only have meaning if you have my documentation. That's how we ran the network for the last 20 years, and that's how we'll continue running it. And not this time around, it would be pertinent to ensure that 32-bit ASNs were first-class citizens, and that the chances of companies ending up using the same community should be reduced to 0. And I'll show that in the examples how that is a crucial aspect of large communities. Large communities were also specifically designed to be easy to implement. And this was shown because in a short matter of time, in 6 months, many implementations were produced. And another aspect is that our document specifies what a large community should look like in your documentation. For instance, with extended communities, there are many ways to notate an extended community. With large communities, we specifically promote one canonical way to ease our operations. So even if you're writing a large community in a particular format for a particular type of device, there is only one way that is promoted as the way to interact with each other in our documentation or in phone calls. Things that were out of scope. There is no mapping system between classic communities and large communities. I meant to say there is no standard mapping system. I think many networks will use classic communities and large communities alongside each other and support both of them at the same time. And each of those networks has to decide for themselves what a useful mapping system is. For some networks, the mapping system could be to use the literal classic community values inside large communities. For other networks, they might want to do some mathematics. Another aspect is there is no type length value or header or any types. With large communities, there's only one thing, and there can never be more. This aspect of BGP is not extendable. So what you get today will be exactly the same thing as what you get 10 years from now. And finally, this is not a substitute for well-known communities. For instance, the well-known communities, no export or no advertise, they are still what they are in classic BGP communities. Large communities does not replace those. So this is a large community. It is a 96-bit construct, or 3 times 4 bytes, where the first number, this is called the global administrator. And then the second chunk of 4 bytes is local data part 1, and it's entirely up to you how to use those bytes. And that is followed by the final piece of the community, local data part 2, yet another 4-byte construct, and you can define that yourself. And the way you would notate these in documentation is number, colon, number, colon. In a way, you could think of this as me function parameter, where me is your ASN, and the ASN of the entity that defines what the community means. The second part is a function identifier. For instance, we could say the number 4 means prepend 4 times. And then the third part, a 32-bit field, is the parameter. And you could put, for instance, a AS number there. There's a document called Large Communities Usage. And if you're looking for ideas how to use large communities, this document should give you some inspiration. Now let's look at some examples where we compare classic communities with large communities. The first example is an example that currently is in use in NTT's network, and it triggers a function in the network that says, do not advertise to that specific AS number in North America. And the astute observer might notice that in the RFC 1997, the classic communities column, we see 65,400 colon, and then the two problems with this. First, we're using a private AS number in what is supposed to be a field with global significance. The reason we're doing this is because we simply ran out of community space. So we started stealing private AS space in hopes that it doesn't collide with other networks. And should there be a merger or an acquisition, then this type of routing policy could result in a problematic situation, because there is no guarantee whatsoever that other networks are not using these values as well. The second issue is that in the peer AS field in classic communities, we cannot fit a 32-bit ASN. So this traffic engineering feature only works for 16-bit ASNs. And given that 20% of the default free zone is 32-bit ASNs, you can see that there is friction, that this is not a good position to be in. Now, with large communities, those two problems are addressed. The first bit is the global administrator. It's entities ASN 2914, and that is ours. Each of you will use your own ASN there. And you can put a 32-bit value in that field. So that means that 16 and 32-bit ASNs get exactly the same type of feature. There is no collisions whatsoever. Then the second part is that same function. Do not advertise to a peer ASN in North America. And the third part is the parameter. And again, we can fit a 32-bit value in that field. So this means this feature will apply to both 16-bit ASNs and 32-bit ASNs. So this is a lot of operational challenges resolved in a single construct. The M6 route servers have a similar traffic engineering community. They have 0 colon and then peer ASN. Again, 0 is not their ASN, so they should not be using it, but they ran out of space as well, so this is what they ended up doing. With large communities, they would put their own ASN in the first field, which is 6667, and then whatever follows after that, that's what M6 is responsible for. And in this instance, they could define 0 as the function that is do not export to this autonomous system number, and then in the third field, again, the parameter. And you can see that for each and every classic BGP community, we now have a chance to improve the functionality and ensure that there is no collisions when operating this in the real world. If we look at the progression of this internet standard, on September 2nd, we published the first internet draft. And then roughly 15 versions later and thousands of emails, on February 16th, this was less than 2 weeks ago, it became an official RFC standard. And the road was not without challenges. In September, IANA assigned a value, a code point to this large communities effort. And unfortunately, we discovered that that code point was already used by somebody that did not have permission to use that code point. So this company stepped forward and had to apologize. And then interestingly enough, many other companies also stepped forward and said, oh, we're also stealing code points. And this resulted in the deprecation of 6 code points because 3 vendors admitted to working outside the IANA registry. And it meant for large communities that large communities had to get a new code point to progress. But that's a better story for a beer at the bar. The important thing here is that large communities is actually ratified as an RFC. And this means that you can go to your vendors and point at the RFC and say, I want this feature. And we had to celebrate. It is I have the feeling that I lost 10 years of my life trying to fight for large communities, which was in order. So if we look at the various timelines, the first piece of the puzzle, getting it standardized, that's now done. Great. The second piece of the puzzle is getting vendors to implement support for large communities. And by vendors, I do not mean just Huawei or Cisco or Juniper. There's a whole ecosystem that depends on communities. And thirdly, we as network operators, we have to start using large communities when we receive the code from the vendors. And a lot of these trajectories are in parallel to each other. If we look at implementation status, at this point in time, iOS XR has a beta release, and they are expected to give a production quality release in the second half of 2017. BERT, a very popular route server software, already supports large communities in its current release. ExaBGP, a BGP injector often used by DNS operators to inject anycast prefixes, supports large communities. Quagga, free-range routing, FreeRouter, OpenBSD, GoBGP, all of those support large communities today. And that is excellent news. Juniper is expected to provide support in the second half of this year as well. If you go to largebgpcommunities.net/implementations, you can see an up-to-date overview of all the manufacturers that we are aware of and their large community support status. And this list is being updated as news comes in. So given the fact that in the second half of this year, we will get software from the majority of relevant vendors in internet routing operations, I dare say that 2018 will be the year of large communities. That is where we should see large spread adoption. But the BGP speakers are not the only component in this puzzle. I think a great example of a piece of software that also needed updating is PMACCT. This PM accounting software is used to correlate BGP information with flow information to construct a matrix of your network of where traffic comes in and where it leaves your network. And PMACT is, to me, a prime example of an important part of the ecosystem that was neglected in the other community efforts, like flexible or wide communities. If you want the ecosystem in its entirety to function, then each of these needs to understand the concept of meta information. And it's not only PMACT, TCP dump is also important, or Wireshark, or BGP dump. All these, everything that uses classic BGP communities will need to receive a patch to support large communities as well. If you want to look at large communities in action, there are at this point in time a few beacon prefixes, and those beacon prefixes are used to test compliance and verify whether the propagation behavior of the prefixes is what we expect it to be. So if you punch in either this IPv4 prefix or this IPv6 prefix into your router, and your router does not support large communities, you will probably see something like unknown transitive attribute with a hex dump of the actual large community. But if your router does support large communities, you might see something like the below, where the software indicates to you that a large community is attached. See the prefix at all, And if you see that an attribute is attached, if you don't see the prefix, please email me, because there might be a problem that we need to resolve. If you see the prefix and you do not see the attribute, also email me, because there might be something wonky going on, and it would be interesting to debug that. But so far, so good. These prefixes have sufficient global reachability that my family at home is not complaining that we're using large communities on the home prefix. If you are a vendor and you are implementing support for large communities, make sure that it is a first-class citizen. And by that, I mean that the full set of features that you offer classic communities are also offered in large communities. So this means that regular expression matching should work, that you need to be able to match on communities or delete communities or add communities. All those features that we have with classic communities must exist with large communities as well. You will need to extend your show commands. For instance, show route large community, and if a value is then entered, it should display all the routes that have that particular community. As implementer, you will need to engage with your sales force, and you will need to teach people that large communities exist and how they are used. On the network operator side of things, it would be good that if you use a particular piece of software and you use communities today in that software, that you email the vendor saying, hey, please add support for RFC 8092. And maybe they'll respond to you like, oh, cool, we never heard of this effort, we put it on the roadmap. Or maybe they'll say, we're not interested. In that case, you should try and see if you can apply a little bit of commercial pressure to make sure that they end up doing the right thing. We will need to update our provisioning tools. All the templates that generate our router configs will need to be revised and extended to support large communities. And we need to update public documentation. We're going to live in a world where classic and large communities will exist next to each other for the years to come. So documentation will need to be updated what both of those community approaches actually accomplish in our respective networks. So do not forget to train your staff and make them aware of this effort. Set up a lab, give people access to the lab equipment, and allow them a chance to work with large communities. So this presentation is now concluded, and it's been an intense journey, but I can tell you now that 32-bit ASNs, for the first time, are now first-class citizens too. And I think for the growth of the internet, this is an important milestone, because for many, many years, I think 32-bit ASNs were neglected and not offered the same tools as normal community use, 16-bit users were allowed. But that is now over. 32-bit ASNs stand a chance. Are there any questions regarding large communities?
About because by that, more control BGP. Better to have more monitoring on BGP system. So like BGP MOM or route views or RIPE list project. That's my comment.
But there was no question, right?
No question.
Okay. Okay. Thank you.
Thank you very much. So it's okay. Yep. Thank you very much. So let's invite the third speaker. So the name should be Sho Fujimura from Fukuoka University. He will present about NTP service And this study was done with Fuminori Tanizaki. He is from NTT West. Yes, please.
Okay. Thank you, Mr. Matsuzaki, for your introduction. Good evening, everyone. I would like to thank you all for attending this presentation. I'm very pleased to meet you all. My name is Fujimura, and I'm with the IT Center at Fukuoka University. Today, I'd like to introduce the Fukuoka University NTP system. I deeply appreciate the opportunity to make this presentation. There are 4 main points I'd like to talk about in this presentation. Firstly, I'd like to introduce Fukuoka University and our objectives. Next, I will outline our university's NTP service and our objectives. Next, I will outline our university's NTP service and describe past examples of malfunction, the current NTP service architecture, and its traffic analysis. I will finish the presentation with a summary and request. The presentation will take approximately 25 minutes. Firstly, allow me to introduce Fukuoka University and our objectives. Fukuoka University is a private university which was established 83 years ago. It was connected to the internet. The AS number is 18148, and the IPv4 prefix is 133.100.0.0/16. The IPv6 prefix is 2405:BE00:/32. It is located in Fukuoka City, Japan. Does the name of Fukuoka City ring a bell? Yes. Apricot 2015 was held in Fukuoka City. I hope you all can visit again someday. We look forward to welcoming you again. Getting back to Fukuoka University, it has 9 faculty, 10 graduate courses, and 33 specialty courses. The number of undergraduate and graduate students total 21,000. It has 2 university hospitals and 2 attached high schools and 1 attached junior high school. Today, I would like to talk about 2 objectives. The first is to ascertain the reason for the increase in NTP traffic. The second is how to decrease NTP traffic. Let me explain about Fukuoka University NTP service and its background. The Fukuoka University NTP service commenced in October 1993. It was the first public NTP service using GPS in Japan, and the IPv4 addresses was 133.100.9.2 and 133.100.11.8. After the service commenced, access volumes increased, and on January 20, 2005, we posted a request to reduce clock synchronization traffic on Channel 2, Japan's largest internet BBS. At the time, we had 900 NTP requests per second, using approximately 2 megabits bandwidth. This diagram shows the network configuration up to August 2015. Fukuoka University is connected to the internet through the Merge Home Connection Environment AS2907 Academic Network SciNet and the AS4713 Commercial Internet Service Provider OCN. Until August 2015, JNTP server was operated in engineering department's laboratory and was connected to the network via an edge switch. The network in the laboratory with the NTP server had a momentary increase in traffic every hour on the hour. It is thought that this was due to the NTP request concentration on. Until August 2015, the NTP server was connected to the edge switch terminal, and this caused network failure at all times. Firstly, due to a previous network failure, was set at a bandwidth of 8 megabits to the NTP server. The router to the AS2907 has no. The reason for this setting is that the firewall went into high load when for maintenance, and the NTP literary packets increased. By the way, the firewall was Juniper Networks ISD 2000. According to the catalog spec, there were about 1 million possible user sessions. The QoS was set at 8 megabits, marking this level. On February 14, 2014, the third NTP server network failure occurred. The traffic from AS2907 to the NTP server increased and put a high load on the firewall, resulting in practically no connection to the internet. We then set the band of the AS2907 to 8 megabits. This result was a slight delay, but internet access was possible. However, the next day, it went down. The reason being that with the increase in traffic from AS4713 to the NTP server, the QoS CPU, and it could not process the increased traffic to the NTP server. In the end, we are able to restore QoS by using L2 switch hardware capable of processing information between the AS4713 and the router and controlling the bandwidth. The QoS was 8 megabits in both the connection router to the AS2907 and the AS4713 connection L2 switch. This traffic graph shows the traffic volumes to the AS2907 at the time of the failure in February 2014. The failure occurred in February, which is the annual entrance exam period at our university. And there were no lectures and few students. So there was little regular traffic. The red line shows the volumes. And you can see the increase in traffic volumes before and after the restoration of the router. I would have liked to check volumes on the 4th, but I have no details. On the 15th and the 16th, the router could not be restored, but on the 17th, just after it was restored, volumes were at about 135 megabits. Subsequently, the NTP server could handle the requests and the volumes gradually decreased. This graph shows the volumes for the AS4713 at the same time. After system restoration on the 18th, volumes went as high as 900 megabits. As I mentioned previously, February is our annual entrance exam period. There were few users and the traffic volumes were low. Looking at this graph, you can see that traffic is normally between 100 and 200 megabits. Thus, we can conclude that most of the traffic at this point in time was NTP. Now, let me summarize the outline of the NTP service in August 2015. We discovered that when the NTP server stops, a massive volume of read-write packets flood in, causing the firewall to stop. Therefore, the NTP request must be continuously returned. The firewall and the BGP router do not stop. And the bandwidth of 8 megabits is set in the BGP router and L2 switch. The bandwidth of 8 megabits was selected because the NTP traffic bandwidth is just below this level. However, we found that, in fact, traffic did exceed 8 megabits. It was unclear at the time how much NTP traffic there was. If one NTP server-related system failure occurred, we had to adjust the 8 megabit bandwidth or drop the NTP request packets. This was the situation until August 2015. Next, I would like to introduce the configuration of and traffic analysis. This diagram shows the university network and locations. From September 2015, the NTP server operations were moved from the Faculty of Engineering Laboratory to the Information Technology Center. Previously, the NTP server was below the firewall, but to prevent network outages in the university network caused by firewall overload, the NTP servers were moved to a location above the firewall. This diagram shows the NTP server network setup. In order to distribute volumes, we have introduced a load balancer. Also, in consideration of load redundancy, we have increased the number of NTP servers from 2 to 4 servers. These 4 NTP servers operate on Stratum 2 and refer to Stratum 1 NTP servers on campus. These 2 Stratum 1 servers gain accurate time from GPS and CDMA and are campus dedicated and not open to public. There are 2 NTP server IPv4 addresses open to the public, 133.100.9.2 and 133.100.11.8. This graph shows the traffic on 133.100.11.8. The top graph shows the AS4713 traffic, the AS2907 traffic. The AS4713 traffic volume is outlined in red marking at approximately 1.64 megabits, where the AS2907 max is approximately 316.22 kilobits. This graph shows the 133.100.9.2 traffic. As before, the top graph shows the AS4713 traffic, and the bottom graph is for AS2907 graph. The AS4713 graph shows a different unit with as much as 164.39 megabits maximum and 8.73 maximum for the AS2907. This averages out to a constant traffic volume of approximately 160 megabits. Currently, the number of NTP packets can be checked on the load balance management interface. The number of packets is shown in the red box. Can you see how many? It's 190,000 packets per second. This packet volume is constantly being sent to the Fukuoka University network. The number of packets is gradually increasing, and sometimes you can detect this level. The up-down throughput is as much as 342 megabits with packet volume at 221,000 packets per second. We tried analyzing NTP traffic using NTOP-NG software. We mirrored one of the NTP server's traffic and conducted analysis using an NTOP-NG dedicated server in real time. As you can see on this slide, showing countries of origin traffic, China was first, Brazil second, and America third, followed by Vietnam, Italy, Spain, Argentina, India, Germany, and Russia. You can see the same trend in AS. As you can see, we get access from countries throughout the world. How did the volumes get so high? One theory is thought to be network device manuals. Allow me to show you one example. This is a manual for a certain network switch, the device time configuration is written as 133.100.9.2, as well as this manual. Many other network devices and multifunction machines have 133.100.9.2 written in them. Also, a number of devices have the Fukuoka University NTP server address as their default. Have this setting are Linux and BGBox-based household use broadband routers and YS-LAN access points. Others include web camera firmware, which had 133.100.9.2 as the NTP server in its factory settings. In the Philippines, which has the Fukuoka University NTP server default. We suspect that this firmware was originally OpenWRT. Allow me to explain why we made this assumption. This is part of the OpenWRT source code from about 2005, and the NTP server setting is 133.100.9.2. Currently, it is in the NTP project settings. The other two NTP servers, apart from the 133.100.9.2, do not connect. Therefore, we assume that commercial packages which are not publicly open and which were based on the source code of around 2005 are still around, and firmware developers are still using it to develop new firmware. So, allow me to present my conclusions. Firstly, let me summarize. Fukuoka University's public NTP service receives approximately 190,000 requests per second. The number of requests is still gradually increasing. Requests come from countries throughout the world. The Fukuoka University network does not desire any increase. And even if we cease NTP service, huge volumes of retry requests will be generated. Therefore, there is no way we can shut down the service. I have a request of everyone. If there are any firmware developers here today, please check your NTP server settings and do not use 133.100.9.2 or things. We request you change them. Next, if there are any manual creators here today, please check your NTP server setting notations and do not use 100.9 or 1. If you find that these are your settings, we request you change them. Finally, if you know any firmware developers or manual creators, tell them about today's presentation. And if they are using 133.100.9.2 or 133.100.11.8, if possible, please introduce them to us. By meeting any of these people, we would like to hold discussions and find ways to reduce traffic in the future. My email is at the bottom of this slide. I would now like to finish my presentation. We would like to find the cause of the increase in NTP traffic and reduce it. We look forward to your cooperation in our endeavor. Thank you all for coming today. Thank you.
Any question and comment? Yep.
Hello. My question is, have you considered finding different addresses server and asking your providers to black hole traffic? Have you considered finding new IP addresses for your NTP servers and asking your upstream providers to black hole traffic to those existing addresses too? Thank you.
新しいアドレスをつけて、古いアドレスは上流でブラックホールしてもらうっていうのを考えましたか？
考えました。答えはちょっと持ってます。いいですか？Okay, thank you. The NTP traffic decreases when an ISP sets ACL. However, it is necessary for the ACL to be maintained for a long time. But I hear that such operation is difficult in the IPS. We will receive the NTP traffic such as the distributed denial of service attack again if the IPS deletes the ACL by mistake. The ACL is one of solutions, but we think it is important to reduce NTP clients accessing our NTP servers.
Okay. Any other comment? If not, thank you very much.
Hello. So this is a question from the Adobe Connect chat. This is from Ernest. He says, you can terminate the NTP service at any time. That is not a free NTP service. Also, why don't you set ACL to block outside NTP inquiry?
Actually, that's the same question, right? So he already answered that. Thank you very much. Okay, thank you very much. So that's the end of the Apops 1. And I have an announcement about this social tonight. So the first bus to the venue will leave like 6:30 from the lobby.